Today we're going to introduce chemical bonding. So there's a couple things we have to talk about before we get into it, and the main question is, why would two elements bond? Well, they bond because both elements are going to get something that they want out of it. What they want is to gain or lose electrons depending on the element, and the reason they want to do this is to become stable, otherwise known as lower in energy. So atoms like to be low energy because low energy means you don't have to do a lot of work. High energy usually means you have to do stuff with that energy, and so it's typically better to be stable by having low energy. Now, we're going to be showing chemical reactions here, so one thing I want to mention, chemical reactions are always separated by an arrow. The stuff on the left is called the reactants. You can think of it as the starting material or the things that goes into the chemical reaction, and the stuff on the right is what we end with. It's what comes out, and it's also called the products. So we'll use the term reactants and products quite a bit. So as a general rule, there's a saying, it's called BARF, B-A-R-F, and what it stands for is breaking bonds absorbs energy, forming bonds releases energy. So this is generalized, obviously it can flip, but 99% of the time when bonds are being broken, energy is being absorbed. We call that endothermic. Now, it can be visualized or written out two ways. You can write it out like this. So this would be H2. This is two hydrogen atoms bonded together. So it would be drawn like this. Hydrogen atom 1, hydrogen atom 2, the line between them is the bond. If we add energy, that energy goes into the bond and makes it break. Therefore, the atoms absorb that energy, and now they are separate atoms. So here we had a molecule of hydrogen, and now here we have two hydrogen atoms. All right, so that's how you could do it. So forming bonds releases energy. We call that exothermic, and here's how it works. Here I have two hydrogen atoms. They're individual. If I let them form a bond or come together, energy gets released. That's why I have energy off to the side on the right side. It's basically saying by forming this bond, energy is released, and that's why the energy is on the right. That's another way of saying it is energy is a product. It's coming out of the reaction, or it's what we end with. All right, so the main thing we're going to do today is called the Octet Rule. So the Octet Rule is the rule of 8. It's pretty obvious in the name, and it pretty much says that all elements, there are some exceptions, want to have 8 valence electrons to become stable, and this is true the vast majority of the time. Stable elements have the same configuration as their nearest noble gas. So I'm going to introduce noble gases in a second to explain what that means. Basically, noble gases are the elements in group 18, which is the far right of the periodic table, which if I have a reference table out, I can show you. So these are your noble gases right here. They are from helium straight down. They all, not these guys at the bottom, but so from helium down to this UUO thing, right? And they all have 8 valence electrons. So if we look at their electron configuration, starting at neon, ends in 8, they end in 8, they end in 8, ends in 8, ends in 8. So they all end in 8 except helium. Helium's going to be the exception. It is a noble gas and it is stable, but it's so small that it doesn't have room to fit 8 valence electrons, so it only actually has 2. That's why I said almost all electrons end in 8. The ones that are closer to helium, the smaller elements will go to helium, and they'll actually go to just 2 valence electrons to be stable. But basically, since these elements are all stable, they're called noble gases. They don't need help from anybody. All the other elements on the periodic table are trying to get their configuration to match these because these are the stable configurations depending on how many electrons you have. And that's why we say they all want to look like their nearest noble gas. So noble gases, they're group 18, they're all stable, they all have 8, helium's the exception. They don't form bonds. And because they have a stable configuration, they don't need to gain or lose electrons, which is the main reason atoms would form a bond to begin with. So therefore, these guys don't bond at all. All right, and the Octet Rule, and this is the first time you're going to see this, is what causes the numbers that everyone mistakes for charge. They cause the first oxidation state. So these numbers in the top right-hand corner that I've been telling you to ignore pretty much all year up until this point, now we're going to explain what they are and what they mean eventually. So here's the rule for valence electrons, all right? Atoms that have 1, 2, and 3 valence electrons are going to look to give them away. And then atoms with 4 or more valence electrons are going to try to find more to go up to 8. So now we said they all want to end in 8. So gaining to get to 8 makes sense. But losing to get to 8 tends to throw people off. Let's look at an example. So an example would be Al. So Al has a configuration of 2, 8, 3. So if Al were to give away 3 valence electrons, then its new configuration would just be 2-8, it would end in an 8, it would look like neon, it would be stable. Whereas Si has 4 valence electrons, it could either give away 4 or it could gain 4. And so it turns out, just like rounding, 5 or more, we round up to the nearest 10. 4 or more is halfway to 8. So it turns out when they have 4 valence electrons, they try to gain to go up to 8. And then if Si were to gain 4 valence, it would become 288, and it would look like argon. I'll explain that more as we go, but so let's get started with this. So here I have the elements from sodium across to argon. So that's an entire period on the periodic table. So it's from Na straight across to Ar. And these are the configurations. So the octet rule says 3 or less, you give them away. 4 or more, you gain. So maybe I can color code it a little bit. So this should make it a little bit easier. And I'm going to leave 8 off, or maybe I can use 8 for a different color, but they have 8. They don't do anything. Okay, and so here's how it works. Elements with 1, 2, or 3 valence electrons are going to want to give them away so that they can go down to 8. Most of the time, there are some exceptions. I will talk about them in a second. But so sodium is going to want to give away 1 so it can become Na28. When it does that, it will gain a charge, and you should know how to do this already. Its charge would be +1. When magnesium becomes stable, it's going to want to give away 2. So it can also become 2,8, and because it gave away 2, its charge is +2. When aluminum does it, it wants to give away 3. It would become +3. So that's the ones that lose. Oh, there's a mistake there. Okay. Now, Si has 4 or is more than halfway to 8, or is halfway to 8 in this case, and so Si is going to want to gain 4 and become -4, because it's going to gain 4 to become stable. Phosphorus is going to become 288 by gaining 3, and it's going to become -3. S is going to become 288 by gaining 2, it becomes -2, and Cl is going to become 288 by gaining 1 and becoming -1, and argon doesn't do anything because argon already is stable, so you could either just write stable, you could cross it off, or you could just rewrite what's up here down here, and it would be the same, it would be 100% identical. All right, and that's how the octet rule works. Now, there are the exceptions. The exceptions are elements 1 through 5. So elements 1 through 5 are hydrogen, helium, lithium, beryllium, and boron. And the reason they're exceptions is because those atoms are too small to have 8 valence electrons. The first orbital, if you remember, there is a limit to how many electrons can fit in orbital 1. The limit is 2. So they are going to want to gain valence electrons. And I actually think, yep, I think I technically have a mistake here, but that's all right, we can fix it. So let's start. Hydrogen has 1 valence electron, so this is why it's an exception. If it gave away 1, it is going to have 0, and 0 is not good. So hydrogen is the exception. Maybe we'll put a little star on it. It's going to gain 1 and go to 2, just like helium. And when it does that, it'll gain a -1 charge. And again, the reason it can be stable with just 2 is because it's so small. And helium is an exception. I mean, helium is a noble gas. It doesn't do anything. It is one of the few, or the only one that can be naturally stable with just 2 valence electrons. And then those are the real exceptions, all right? And then the rest follow the rules. In other words, in terms of gaining and loss, the rules are followed. Lithium is 2, 1. It can either lose 1 and look like stable helium, or it could attempt to try to gain 7 and look like stable neon. It's clearly way less work to give away 1, to find 1 to be given away, or to have an element take 1 away than it is to try to take 7 away. So lithium is going to look like that. It's going to go to 2, -1 charge. Be, common mistake here. I'm not going to put a star on it because it doesn't behave different from my gain and loss sequence, but the common mistake here, if you haven't already seen it, saying, well, Be doesn't do anything because it ends in 2, just like helium ends in 2. But that's not true. Helium has 2 electrons in orbital 1. Be has 2 electrons in 2 and another 2 in orbital 2. Orbital 2 can fit 8, so this is not a stable configuration. So Be is going to go to 2 as well with a, oh, I made a mistake here. +2 charge. So we've got +2 here, and that one was supposed to be +1. All right, so that's a common mistake there. B is going to do the same thing for the exact same reason. It's also going to go to 2, and it's going to go +3. All right, and then once we get to carbon, they're going to gain. So carbon, we can do this a little faster if you take a look. -4, -3, -2, -1. And also, you should see a pattern. If you look at the second period on the periodic table, and then you look at the first period on the periodic table, the elements in group 1 all went +1 because they all end in 1. The group 2 end in +2 because they all end in 2. When we go over here to group 3, they end in +3 because they all end in 3. 4, they all go -4 because they end in 4. Group 15, we're nitrogen down, they all end in 5, so they're all going to go -3. Oxygen down, they're all going to end in, they're going to have -2 charges because they all end in 6, they need to gain 2. This group all ends in 7s, they need to gain 1, so they'll go -1, and then this group won't do anything because they're the noble gases. So you can see there's a pattern, and what I mentioned before, and I'll explain it one last time if you didn't already figure it out, the oxidation states, those numbers in the top right-hand corner that I told you to ignore, they are the charges that the atom will take on when it becomes stable. So if you look at sodium, it's +1 written here because when it satisfies the octet rule, it wants to go +1. Magnesium will be +2. Aluminum will be +3. Now we get to some interesting stuff. Si, if you notice, there's multiple oxidation states present, but the first one is -4, which is what we would expect. Now the issue is there are other ways to become stable. That's why there are multiple. Like if you look at nitrogen, there's a ton of oxidation states, right? But the first one is -3, which is what we would expect because it ends in 5 valence electrons. The other ones we're effectively going to ignore, okay? Because there is ways of becoming stable that don't follow the octet rule, but those are 1, too advanced for us, and 2, very rare, and so we're not going to really talk about them much. And that's why we're only really going to be paying attention to the very first oxidation state. And also notice I skipped over this entire group here. They don't follow the octet rule the way you would expect them to, which is why I originally called them group 1, group 2, and then I called it mistakenly 3, 4, 5, 6, 7, 8, because on old periodic tables, they used to actually make these 1, 2, and then 3 through 8, and then they would call these in the middle something different because they didn't follow the same rules. The new table is updated a little differently, and so they call them 1 through 18, but whatever. As long as you look at the valence electron number and you know what they're going to do to become stable, then that's all that ultimately matters. And also notice the pattern. It will make your life very easy because, again, if you know what oxygen wants to do to become stable, then you also now know what sulfur, selenium, tellurium, and polonium want to do to become stable. And so once you know the pattern, it will make everything much easier when we use elements that you might not be as used to. And that is everything for this intro lesson.